Okay, good day to you all. So today we are going to talk about fuzzy sets and fuzzy logics. These fuzzy set and fuzzy logics are a continuation of this classical sets that you already know and you have learned in your levels and A levels. Let's see what is the difference of the fuzzy sets and how to use them in machine learning. So first of all, we need to refresh our memories about sets. So first, we have to have the concept of a universal set in here, which it denotes by X, and the elements are simple X. So capital X is the universal set, and it represents all the elements that have in a set. Then this is the notation that we can write, which can be used here. Then by this notation, this is showing that simple x is an element of capital X. So that is how we are writing it belongs to one of the sets. Then, so the elements can be presented as each and every single element, or we can go like a, uh definition. So in here, capital A was defined as all the natural numbers. So these elements, the x can go from 1 to infinity. So all the natural numbers are there. There can be other sets. It can be like any of the uh, complex numbers. It can be primary numbers, or likewise, it can be any of the numbers. So if we show in a diagram, we can draw like this. Let's have, so let's have the universal set. This is X that we have, and then we draw the subset A, which is the natural numbers. So in here, let's add numbers like uh, 1 to infinity. So this is X, capital X, and this is A. So that is how we denote these two sets. That means universal set and the subset of A. Another definition that we have is um, the characteristic function or membership function. That means, let's think that x is the natural numbers and we have 1 to 10 in there. Then a is prime numbers. So we only have 2, 3, and 5 and 7, right? I think I'm right. So in here we have 1, 2, 3. So 2, 3 is not there. 1, 2, 3 not is there. 4, 5, 6 is there. 8, 9. So these are the numbers that we have in the um, universal set. So if we consider the universal set, um, we have 1 to 10. So then we define f a x, which is the characteristic function. This characteristic function can be can written for the primary numbers. So 1 is not a primary number. Before this, I think it's better to write x, so you can see better. 1, 2, 3, 4, 5, 6, 7, 8, 9 are belongs in the x function. So then we write the fx. So 1 is not a primary number. 2 is a primary number. 3 is a primary number. 4 is not a primary number. 5 is a primary number. 6 is not. 7 is. 8 is not. And 9 is not. So this is how the f(ax) function look like, or the characteristic function, or the membership function look like when it comes to the sets. So basically it is showing that a subset A, so this should be A, capital A. This should be capital A, sorry. It's not editable. It should be capital A. So likewise in here, the notation. So this membership function shows that whether this subset A has this element or not. So it is only giving 1 to the elements that it has in this subset. So let's move on. In here, we have shown the notation. If A is a subset of X, it write like this. Then there are two important concepts, intersection and the union. That means if there are two subsets and one element belongs to both subsets, it will be represented from this area. Then the union shows that if there are two subsets and all element belongs to these two subsets denoted by this notation, the union. So that is one of the most important concepts. So another one is the law of non-contradiction. That means we have a set again like this. I'll draw like this. We have set, and this is the universal set, and this is A, or the subset. We have A and A complement. That means outside of the A. So if A is belongs, some elements are belongs to A, and some elements are belongs to A complement, and we can say that the intersection of these two are null set, or there are no elements there. That's because there cannot be any elements in the boundary belongs to both of the sets. And the other one is if A union A A union and sorry about that. So A and A prime, if we have the union of that, we can have the X or the universal set. So that is the concept of or the logical laws of sets. Okay, let's move on. Okay, this is what we already discussed, the logical laws. So then we will be talking about the fuzzy sets. Fuzzy sets means uh, it is not a binary representation like the classical sets, and you can have the uh, membership information. That means we will be discussing that with the examples, but not the binary whether it belongs to this set or not. Like it is 1-0 representation in the classical sets, but in here we will be having the decimals, whether it is half belongs to this set or that set. So it can deal with some sort of uncertainty whether we will be getting exact numbers or not. So in here we have the definition. Actually, first we have the element, then the membership information of that element in the second level, and the simple X is it should be like a classical one. That means the element it should be belongs to universal set. Then membership information, the it can be any number from 0 to 1, including 0 and 1. That means all the decimal numbers can be there. So in here, this is actually not the integral. This is just a notation. Uh, this is how we write each and every element of the fuzzy set. So we have like in below, we have capital X, that means the element, and then the membership value of that element in on top of it. And we will be writing that as the fuzzy set. So we will be considering this as a following set, and we will consider the classical definition that we discussed earlier. So if A is a subset of X, and we define A as set of neighbors of 30. So in here we have 30 and we have neighbors 12 and 14. So since 13 the 11 and 15 are not exactly next to 13, they also can be neighbors, but in here we cannot consider that. We only have a binary representation. We can say that it is a neighbor or not. So we have to choose these two as with the classical definition as the definition of set of neighbors of 13. So for the A, we have 12, 13, and 14 only. But then we have the fuzzy definition. When it comes to the fuzzy definition, we can say like, although the 11 and 15 are not right next to 30, it is some kind of neighbors. You are not like when it comes to a road or a lane that we have, we only not deal with we have a road like this, and we have houses like this, few houses. We have few houses, and from there we have the house number 30 in here, and we have they are very close neighbors 12 and 14, but this house has neighborhood in here as well. In 11 and 50, we can call them their neighbors. They are not exactly right next to them, but we can say like, yeah, they are neighbors. So in fuzzy definition, we are giving them a value. So 13, 12, and 14 has 1 on top of it as the denominator. Uh, so they are like full neighbors, or they have the most probability to be the neighbors. But then 11 of also 0.7% or 0.7 value neighbor. Then we have membership value of 0.4 for 10 as well, because although 10 is here, it, it is just 2 blocks away. So we have 2. Now, so we have 4.4 here, and even 17 after few houses away, we have given them 0.1. So likewise, we can have a fuzzy definition of A with this kind of set. Let's move on. Okay, in here we have said that this is the membership and this is the elements that we have. So another example, we can say we have marks M, marks here. Let's have capital M here. Okay, this should be capital M, not the X. We have marks from 45 to 93, and we need the set of average marks. And we consider the exact average mark is 70. In here we have the 70. So when we consider the average mark for the students, what they have scored, we have few students that we can have 1 or 2 students that exactly score 70. But there can be students that scored 64, 71, 72 likewise, very close by 70, but they are not exactly the 70. So A is a subset of M, and M is set of average marks. But the thing is, we cannot say that like even after 60, 64 or 60, we can say like 59 is even average, because it is a little bit far away from 71 likewise. So we can define as users what is the range that we are considering here. In here, we have considered from 60 to 70 and 70 to 80 are like average marks. Let's see. Let's think like this. We have 0 here. We have 0. We have again 60 here. We have 70 here. We have 80 here. And we have 100. Now, we will consider about values like this. Okay. So 70 is the highest value. We are giving it to with 1. Value of 1. Exact value is 1. Then from 1 to 60, we have linear increase or decrease from 70 to 80. So since we have 10 numbers and we are going from 1 to 0, we can divide this by like each number, like for each one number that we are going away from 70, that can be 69 or 71. we are reducing 0.1 from the membership value. So when it comes to 64 here, we are getting 0.4. And when it comes to 71, it's just after 1, 70. So 1 away 70. So it will only reduce 0.9. In 72, it is 0.8. But after 80 and after 60, we don't consider them as neighbors or the averages. So they will get zeros. In these two, they have got zeros. So because of that, we can say that only these numbers are the averages, and we have membership values of these numbers for this set. And the other thing is, we can define that whether we are going for like 60 to 80 or 65 to 75 or 55 to 85, the average, because it is totally dependent on the use case of this application. So don't worry about that. Just go with the application and the use case of this fuzzy set. So last two fuzzy set, we have used two definitions to select the membership. But in here we have list down few of them: similarity, intensity, probability, compatibility, or approximation. In here we can say the distance as well, distance from the mean, likewise for the membership. So now we need to discuss about how to represent these fuzzy sets. Now we know how to write it, but how to represent. First, we represent elements in the x-axis. So from 0 to the max value, from min to max value, we will put the elements from here. And the membership from 0 to 1, we will go for the membership. And we are getting like a few examples. For the last time, I draw the triangle. The membership values are starting from 70 to 80. Likewise, in here, we have minimum to x value, we have 1. In here, we have x. So we have 1 altogether. Then we have linear decline to another value. So this is how we represent the membership and the elements in a fuzzy set. Let's look at a few examples in the next slide. You can say this is the one I already discussed. This is the one I drew in the first example, in the marks example. You can see like from here to here, this can be 60 or 70. You can go 0, because with our application, it is this area should be 0. Then we have linear up and down, or increases or decreases. Then from some number onwards, it will go again 0. So as I said, this is you can adjust this according to your use case. This is about the house problem that we had earlier. If you remember, like we had three values with one, that with very good membership values and the perfect values. So other than that, these other houses got lesser values. So we can represent that 1 to 7, there are no uh, membership numbers or memberships. Then at 7, even in 7, it is no. But from that to 12, 12 got perfect score. It is increasing linearly. Then 12, 13, and 14, we got perfect membership values. And then from 14 to 18, it is getting again lower and lower. And at 18, it becomes again 0. So uh, if we have 1 to 20 there, up to 7, it is 0. Up to 7 to 18, we have some number with the calculation, with the linear calculations. Then 18 to 20, again, it will be 0. This is another example that has the marks, and you can see in here 60 to 80 is in the range of averages, and others are 0. Then the representation of the complement. In the classical set, we had few rules about the complement, and in here we will be using another some calculations that we need to do to represent the complement. So in here, complement is calculated using 1 minus the membership value. This is always the value, the sum of these two will be 1. So it has like a relationship like this. You can see the membership values are increasing. Sorry, it is having same number, or the confidence of 1 up to 1 point, and then it declined. For the same numbers, the complement goes 0, and it will go up, and it will go to 1 when the membership values are going to 0. So that is how the graphs are there. And before moving to this, let's think about a triangle like this. I'm going to draw here. Okay, we have values. These are like guidelines that I want to do the drawing. Okay, so this is how it comes. Up to 60, it is 0 for membership function. And in here, it will become 1 for complement. And from 60 to 70, membership function goes to 1, and that point, this will become 0. And again, membership function will comes to 0 at 80. That means it will go to 1. And at the end, it will become 1 when it is 0 for the membership function. So this is how the complement of membership function works for this kind of graph. Okay, there's another thing that you needed to know. In the classical sets, there's a clean boundary between one set and another. And uh, if there's an element in one set, it couldn't be in that it is complement within its complement. So the problem in here is if we consider this x value, these are the elements. If we consider x value, it is inside the membership function of A, as well as it is inside the complement as well. So you can see in this triangle, the values within this triangle belongs to both this membership function and complement function. Likewise, the values are in here is not belongs to any of the complement or membership functions. So because of that, uh, we the classical rules of uh, these two, that means complement with A and A complement your intersection is null, that is not correct for fuzzy set, and A and A complement union of that two sets are not equal to uh, universal function. So that is a thing that you should remember when it comes to the fuzzy sets. Then when it comes to the fuzzy set, you need to measure the fuzziness of the fuzzy set. For that, you have this equation. Um, you will be taking minimum of either membership function or the complement when it comes to this kind of set. We'll take in here the minimum value is 0, in here 0 0, in here 0.25, in here 0.5, in here again 0.25, 0 0 0 0 0. Likewise, the value of the minimum value of the from these two numbers are taken to the sum. Then we will take 2 over n value, or the average. We will calculate the average value and multiply it by 2 for the fuzzy set. Okay, I have a small question for you. You can check whether why there's 2 in this equation, and keep that in mind. Okay, let's move on with this. So we have a small example. So you can see this, excuse me, sorry. Okay, we have calculated these numbers. Again, like the previous example I have shown, we have taken the minimum number from each, and we have sum up them, and we got 2.4, right? So we have used the equation here, and we got 0.436. That is the fuzziness of this fuzzy set. So that is the fuzzy sets, and we will be able to check fuzzy logics. Give me a second. Okay. now we are going to check about the fuzzy logics. Now we know the fuzzy sets and how they are working, and what other representations it can be done. So from that onwards, we can use fuzzy logics. What is the use of fuzzy logics and what is the background of it? Um, it is not a part of machine learning up to recent past, because people are saying it is more resource. It need a lot of resources when it comes to fuzzy logic. So since we didn't have that luxury with the old computers, the fuzzy logics were not that much used, but although they have used in control systems by most of the Japanese engineers for bullet trains. When they're using the bullet trains, they have used fuzzy logic heavily. So when it comes to fuzzy logics, I should say like it is like this fuzzy logics can be used to map your um, words into mathematical world. So you might say you might feel when you are going to Candy, it is a little bit cool, but you don't know the exact temperature. Then you move on to the Norelia, and this is usually extremely cold. Oh, it is not easy to be there. And you can compare from each one by one, but you cannot say exact numbers. So when we take input from human, they are like to give inputs in like verbal manner. So in here, we will be matching them, like we have the exact temperature with us. Then we feel it and we will give you a response based on that input. And there's a fuzziness in that answer, then we will be reverse engineer that, and we are trying to get the exact values with that answer. So let's see how it is done. Before moving that, uh, we need to know about saturation and dilation, or concentration or and dilation. You know, the membership numbers that we have is in between 0 and 1. That means decimal numbers. When it comes to those decimal numbers, if you take the square of those decimal numbers, it will be getting low and low. It will be going in a line like this, a saturated line. And again, if you take square root or 1/3 of the power, uh, it will be go in a line like this. It is like dilated. Even though we are not discussing heavily on this topic in this module, you need to have a little bit of understanding about this. So we have memberships of is known as hot, cold, cold, and if if you want to say it is very hot, what is the part that you have to use is concentration part. And again, you say it is very, very hot. That means it's more hotter than concentration. So again, you use concentration like this. And you say not very hot. It means it's hot, but not very hot. That means are taking the um, you are taking the complement of that concentration. And finally, it says less hot. That means you are moving into the dilation. And if you want to say very, very less hot or less hot, it is dilation again dilation site, dilation like this. In here we use concentration and we will move into dilation like this. So that is how the notations are there. Okay, let's talk about the fuzzy logics. And in here we have already discussed in the automotive industry, especially in bullet trains in Japan, the fuzzy logics is heavily used when it comes to brake systems and everything. Then transportation, well, when we are doing transportation heavy goods, we'll and human, we'll use fuzzy logics. Then speech recognition. You are very familiar with NLP, with modules, but in previous years, the fuzzy logics has used for speech recognition. Then ATM machines. ATM machines has to be decided whether you should put the card or give the money away and give your card back and give your printed bill. So for that, not all the ATM machine, but most of the ATM machine use these facilities. And in home consumer electronics and decision-making system, especially in NATO system, has AI based decision-making system. So fuzzy logics is part of machine learning, and machine learning is part of AI. So in these decision-making systems, you have to take like NATO is using this facility and entrepreneurship. Not the entrepreneurship when it comes to like banking. You can decide this using this facility whether this person is good enough to give a loan or not. Likewise, these facilities can be used everywhere without knowing us. So then these fuzzy logics uh, can be used extensively for the variables that not numbers. If you are not getting exact numbers, I already told you like when it comes starting from here, we can say Colombo is very hot. Then we are going little bit of Peradeniya or no, Candy area, we can say, oh, it's cool. Then again, to Nuwara, we can say it's hot again. Sorry, it's very, very cold again. And then you go down to Ampar side and Batticlaw. You will say like again it's getting hot, and at the Batticlaw it is very hot. So likewise, we can say the how we feel by words and sentences uh, that has to be understand by the natural artificial intelligence. That when it comes to artificial intelligence, they don't understand these words, but we need to translate them that they can to a language that they can understand. So these linguistic variables can be used for many machine learning applications using fuzzy logics. So when it comes to fuzzy logics or the linguistic variables, we need to know five terms or five definitions. We need to know variable name, set of terms, universe of discourse, syntax rules, semantic rules. So let's start with an example, and I will explain these one by one. So we have temperature. Now I told you like there are exact numbers in Colombo. You can measure that the temperature is 37. Then it comes to Peradeniya, you can say it is around 27. But when it comes to the Norelia, it is around 30. So there are exact number. So temperature is exact value. Then we have set of terms. That is how we describe this, whether it is very cold, cool, warm, or hot. So we have six terms here with uh, the temperature, how they feel. So there should be a connection when the temperature is changing. It should match with this set of terms. So there should be a rule. This what we call the syntax rule. So by the syntax, the temperature match with how it feels for us. Then some people feel very cold even at -10 Celsius. And all of them feel very cold until -26 Celsius. So starting from -30 to -10, people feel uh, very cold. Then from 20 to 0 Celsius, they feel cold. From 10 to 10, -10 to 10, they will feel cool. Likewise, each and every person can feel the same temperature in different ways. So when it comes to point in between these, some people can feel it in the higher definition or the term. Some can feel the lower term. So we have to draw again. This is again the membership functions that we have talked a few times in the past fuzzy sets. So this is the same. So we will be using this to universe of discourse. That means the exact values. We will use universal discourse, then we have set of terms, and how they match with each other. Again, temperature and this terms will be matching with syntax rules. So matching with syntax rule. Then again, these set match with the universe of discourse with the semantic rules. So that is how these five terms that comes into play. So consider that the number of -12, it is in here. So I'll draw this one. You have -12 here. And it belongs to two memberships. It is 0.25, that means very cold, for 0.25 people. And for 0.75 people, it is cold. So it belongs to two sets here. When you get a problem, it can be in the exam or any other problem regarding the fuzzy logic, you have to use three steps. First is falsification, then inference, then defalsification. So I will be discussing this in theoretical way. and using example, I'll share another video with you. So it will show you how to do the falsification and defalsification with an example. So it will be really easy. And I'll also share you one of the examples that you can use that has falsification and defalsification. Um, in here, we will be using method of centroids. That means there are few methods that for do the defalsification, and in here we will use in method of centroids. So let's go one by one before discussing that. Okay, now I'll take an example to discuss you about the inputs and falsification. So in here I will be using few inputs for one of the problems that we have day to day. That means we have to turn a car. So if we have to turn a car, there are a lot of number of things that has to be considered. But main three things that we can consider is um, how much speed that we have in the car, or how much the how many angles in the bend uh, in the road on the road. Then third one is the load of our car. It can be one people or five people. So with that also you have to consider how much steering you have to do. So we have to need uh, the output is how much steering you have to do when it comes to turning that specific bit. Okay. So first, for the first input, I'll tell you this is speed of the vehicle. When it comes to speed of the vehicle, it can be going very slowly, like 5 kilometers per hour, 10 kilometers per hour. So it is very slow. So people say it's very slow from 5 to 20 kilometers. Then it is going slowly, not very slow, but slowly. From 15 kilometers to 40 kilometers, they say it is driving slow. Then some people say from average, from 40, 35 to 65, 70, they are going a little bit fast. Then after 80 kilometers per hour or after 75 kilometers per hour, they'll say it's very fast, very, very fast, driving very fast. So um, you can have inputs depend on that inputs. We can say we can define fast, very fast, slow, very slow, or average speed. Then there can be another parameter. What is the angle of the road? So how many degrees that the bend have? So first you can start from straight road to up to 20 degrees. You can say small bend. Then from 20 to 45, 60, it's a little bit 60 degree. Sorry, it is like a little bit higher bend. Then it comes to 90 degrees. It's a very large bend. Then if it goes to 180 degrees, it's a U-turn. Likewise, you can specify the ranges of the bend. So I'll say angle of the road or angle of the bend. Then third one is load. Starting from driver only, that is around 60 to 70 kilometers, 70 kilograms. Then there can be two, three, four, five people. So it can be very less loaded, uh, loaded, heavily loaded. Likewise, we can say uh, we can word them according to these ranges. So each one by one, they are not, we are not entering exact values. We are entering the responses from the users or the human. Then inference. Inference means set of rules. These set of rules can be uh, output of combination of input. In here, we have a table with the inputs. You can say this is the uh, relationship between temperature, rain, and the output humidity. So if we can say if there's a high temperature and no rain, it is dry. If it is warm and it is rainy and it is moist condition. Again, if it is warm and it is heavy rain and it is wet conditions. So we have the set of rules like this. Then using these rules, you have to do, you have to get another set of uh, simple fuzzy logics, and you have to get the sum of that area. It is like it is not that much of complex calculation. I'll go through it. I'll share you a video from YouTube with an example. He is talking about what are the exact defalsification, how to do that, and what is the method that it is using. In here, we are, as I said, we are using centroid, method of centroid. So you will be understanding that using that video. I'll share it with you. So all in one, we have to start from falsification. Then we have the set of rules or the inference stage. And then we have defalsification, the calculation stage, to get back the exact outputs for as numbers. So there's a small example. I'll skip that for now. Then when it comes to machine learning, machine should learn there something. Uh, in here, machine don't exactly learn anything during the training process, but we categorize it as machine learning because we use rules for that. And this is how it went under the machine learning part. So how to get these rules? We talk about in the inference, we can have that kind of tables. So how these rules are taken into the fuzzy logics? First, we ask from people. We ask from the experts how it happens. If this day is dry and there's a rain, how it's going to be the day. Then using traditional machine learning techniques like clustering and uh, evolving algorithms, you find these rules. Then another rising concept is evolving fuzzy rules. Actually, when it comes to machine learning, we have to uh, train new set. If we want to evolve this uh, machine learning algorithm or the output, but in here, uh, if something is changing, we can use evolving fuzzy rules. While it is online, it can change these fuzzy rules online. So that is another concept that we use fuzzy logics or the fuzzy rules. Um, so these are the things that I wanted to discuss today. Uh, to understand the fuzzy logics and how to do, especially to do defussification, I'll put a link to YouTube video and another set of examples uh, will be available on the LMS, and you can use them to understand these rules. If you don't understand anything um, from this lecture, you can drop me an email, and I'll arrange discussion or any kind of discussion with the people if you need. So thank you very much. So let's have next lecture on the next week, and thank you. See you on the next week.